everybody, for 17C. Here is a video similar to a problem for Rademacher's homework number 4. We're trying to find the maximum and minimum of a function, but on a closed boundary. So we're going to look at the function f of xy equal to x squared plus y squared plus x squared y plus 4 on the boundary x and y between -1 and 1, which we often could write like this. You could say that the domain is the set containing x and y such that x is between 1 and -1, y single. And so the first thing we do, as usual, is we find the critical points. So we set the gradient equal to 0. Gradient is 2x plus 2xy, and then 2y plus x squared. Solving this, the first equation, we can factor out the 2x, and we got 2x times 1 plus y equal to 0, so we get x equal to 0 or y equal to -1. Plugging in x equal to 0 to the second equation, we get 2y plus 0 squared equals 0, which leads to y equal to 0. So 0, 0 is a critical point. Plugging in y equal to -1 in the second equation, we get 2 times -1 plus x squared equal to 0. So then we get x squared equal to 2. So x is plus or minus root 2. However, plus or minus root 2 is too big. Our domain is restricted to between x being between -1 and 1, so we actually don't use that critical value. So the only critical point we have is the point 0, 0. However, when you have a boundary like this, you can also have the maximum min at the boundary. It's kind of like how in 2 dimensions, right, if we had, like, say, some function like this, we'd say, oh yeah, there's a relative minimum, there's a relative maximum there. But if we cut it and we just look at, say, from here to here, well, then the endpoints become candidates to be absolute max and mins. We have still an absolute minimum here, and we have an absolute maximum right there. So in the same sort of way, all of the boundary points are candidates to be max or min, so we kind of test those. So what we do is we look at the 4 equations. We're going to be along x equal to 1, y equal to 1, x equal to -1, y equal to -1. And then we just plug those into the function. So on x equal to 1, we've got, I think the function was f of xy, x squared plus y squared plus x squared y plus 4. F of 1 comma y is going to be 1 plus y squared plus y plus 4, which is y squared plus y plus 5. And we know that that's a parabola. Yeah, sorry, I'm looking at some notes and they actually made a tiny mistake, that's fine. So it's a parabola, it's going to have a minimum value at y equal to -1/2, because that's where the vertex is. Or you could take the derivative here, right? Fy equals 2y plus 1, so that equals 0. So you y equal to -1/2. And then, so along x equals 1, it's kind of like how, right, along x equals 1, it's going to bottom out at y equal to 1/2. So like right here, that's going to be the minimum value. So maybe the surface actually looks something like this, right? And it's going to be, right, maybe like right here, that's 1/2, and it's kind of a minimum in that direction. For y equal to 1, you get f of x1 equal to, let's see, x squared plus 1 plus x squared plus 4. That's going to be 2x squared plus 5. That's also an upward opening parabola. It's going to have a minimum at x equal to 0. So here we're getting a min at 1 comma -1/2. Here we're getting a minimum, x is 0, y is 1. If x is -1, we're going to get the same sort of thing. In fact, we're going to get the exact same things we did up here, because the x's are both squared. So x equals -1. You're also going to get y squared plus y plus 5. And you're going to have a minimum, because again, it's an upward opening parabola, at -1, -1/2. And then for y equal to -1, f of x comma -1, if you plug a negative 1 for y, you get x squared minus x squared, so those cancel out. So you actually just get 5. When that happens, that means, right, the function, so the function values, the z values along the line y equal negative 1 are always 5, so it's just constant there, so there's no max or min, there's no extreme value. So now, we're going to make a list of all of our candidates. So basically, here's what we found. We found a point here at 1 comma 1 half, a point at 0, 1, a point at negative 1 half, and when for the y equal negative 1, we didn't find anything, so it's constant. So we look at those points. We also look at the corners, because the corners can be where you have maxes or mins as well. So then we're going to evaluate our function at these 1, 2, 3, 4, 5, 6, 7, 8, because 0, 0 is also a critical point. So just like we do absolute maxes and mins for right 17a, we're going to do it for this way as well. So we take all the edges and we test to see where it's the biggest and where it's the smallest. So we're going to have, let's see. So it's kind of a pain. We have to look at f of all of these points. F of 0, 0, f of 1, 1, f of negative 1, 1, f of negative 1, negative 1, f of 1, negative 1. So this is our one like true critical point where both the partials are equal to 0. These are all where the corners, and then we also have to look at f of 0, 1, f of 1 comma 1 half. I feel like it was 1 negative 1 half. Let me double check that. It was 1 negative 1 half. I drew it wrong. Sorry. It should be down there, not there. And f of negative 1 half. Then we plug those all into this. So plugging in 0, 0, you get 4. Plugging in 1, 1, you get 1 plus 1 plus 4 is 7. Negative 1, 1 would be 1 plus 1 plus 1 plus 4, which is 7. Negative 1 will be 1 plus 1 minus 1. So that'll be 5. 1 negative 1 will be 1 plus 1 minus 1, so I'll also be 5. F of 0, 1 will be 0 plus 1 plus 0 plus 4 is 5. Right? Yeah. So 1 negative 1 half will be, let's see, 1 plus, let's actually write this one, 1 plus 1 fourth plus 1 times negative 1 half plus 4, that's going to be, see, 1 minus a half is 1 half, plus a fourth is 3 fourths, plus 4, so 4 and 3 fourths are 4.75, and plugging in negative 1 half, we get, let's see, 1 plus 1 fourth, also minus 1 half, it's going to be the same value. So we have absolute maxima here at 1, 1 and negative 1, 1. Absolute minima here at 1 comma negative 1 half and negative 1 comma negative 1 half. And yeah, I would try to draw this. I could try and draw it. So here's what I'm seeing. So I was going to try and draw the surface. So I'm thinking like in the xy plane, right? So here's my xy plane, and at 1, 1, it's the biggest, it's 7. Not that you need to drop it, it kind of helps you see. At negative 1, so that's back this way, 1. It's also the same height as 7. So those are maxes, so that means in between there, it gets smaller. So this is along the line y equals 1. Right, so yeah, so it's going to be, right, at 0, 1 is 5, so it kind of does this deal. And then over here, sorry, this is kind of fun now, when x is 1 and y is negative 1, so at 1, negative 1, we have the value of 5, so it's going to be not quite as high up, but it's going to be down there. And, sorry, this is a little bit kind of assuming, 1, 1. When x is 1 and y is negative 1 half, it bottoms out, so like maybe down here. So it kind of does like this, and then kind of comes back. And then -1, -1, we also get 5. That's 5 as well. And I think we said along y equals -1 it was constant. Let me double check. Yeah, right, when y equals -1 was constant. So this is just kind of like a straight line across here. And then when along the line over here where x is -1, you get a bottoming out of negative, so it kind of goes down like that and that. And then I don't know, there's something happening in the middle, right? Where like so this isn't exactly a perfect picture because we have also f of 0. Oh no, f of 0, 0 is 4, but like I can't really draw the little lines to like connect everything, so I don't know. But I think that looks pretty alright actually. So you might try graphing this on Desmos and see what it looks like. So hopefully that is somewhat helpful. That video is kind of long.